In this video, we'll continue the terminology discussion and we'll discuss three terms that will appear a lot throughout the class: SCADA, DCS, and PLC. SCADA stands for Supervisory Control and Data Acquisitions, and SCADA systems are generally used to control dispersed assets where centralized data acquisition is as important as control. So as you can see in the graph on the slide, you have your control center and you have your field sites that could be located geographically very far away from the control center. So through some kind of communication medium, could be telephone lines, could be radio frequencies, could be satellite connection, you connect the control center to the field site. And in the control center, you have your HMIs, as we discussed before. It's the graphical interface the operator sees. And you have your SCADA system, your control server. Through some kind of a communication router, you have connections to the field sites. So here, that can be, for example, this field site 1 could be 50 kilometers away. You have a PLC there controlling some part of a process. And through a modem and some kind of a connection, you connect back to the control center where the SCADA collects the data and presents the data to the HMI and also stores it with a data historian. Similarly, another field site has an IED, intelligent electronic device, that through some kind of a connection, could be the same one, could be different, could be wired, could be wireless, connects back to the control center. So in a way, SCADA is more relevant to geographically dispersed ICS control systems. So you have, let's say, your headquarters of your company and you have your field sites. Power grid is a very good example of such a setup, where you have headquarters of the company and the substations that are located far away, and you connect to the substation through some kind of a communication channel and you bring data in. And that's exactly what SCADA does. It's data acquisition and you have supervisory control. SCADA is more event-driven. So you receive events, you receive information from your field sites, and then humans will make decisions based on the data they receive. So if you see some kind of a problem appearing in one of your field sites, then an operator can make a decision about taking some action to correct the problem. The communication from the main site to the field sites can be in different forms. Here we have, this slide shows some basic SCADA communication topologies as they appear in the NIST handbook. One would be a direct point-to-point connection. So you have your modem from the SCADA to the modem of your field site. That's point-to-point connection. And again, this can be wired, this can be wireless, radio frequencies, or many other ways of communicating this telemetry. So that's point-to-point communication. Or you can have communication in series. So you connect one modem to the other. You have in your field site the RTU, and then these RTUs between themselves could be far away, or they could be in the same location. So in order to reduce the cost and the maintenance of the connection between the main control center and the field site, you may choose to connect the network in series. So you have this connection to this connection, right? This has the benefit of cost reduction, of course, because you have here this link is only one link, and this could be shorter ones. But on the downside, as you can understand, is that if something happens on this side of the network, then the communication after that cannot go through. So everything is also affected based on what is happening on the first node, or the node that's before in the series connection. So there's pros and cons in that topology. A kind of a trade-off between series and point-to-point would be a series star, where you may have a series connection, you have a direct connection to a point, but then you may have more than one connection to individual points. So this could be one-to-one connection here, point-to-point, but then at this side, different modems connect to different PLCs. So this is again a single point of failure here, but if something goes wrong here, this chain won't be affected. And it's not uncommon for PLCs to be connected in kind of a daisy chain. And the last topology that we'll discuss in this slide is called multi-drop. So here the modems are connecting series. So you don't go through the PLCs as we saw in the series one on the series stars. You have a direct modem connection, and then the modems are connecting to the PLC. So you send your message throughout, and if the PLC is unresponsive or is not listening to the commands, then the communication is not affected as much, right? Of course, if the modem has a problem, then you have a serious connection problem. But if here in the previous one, the PLC was directing the communication between in the series nodes. Here you have the modems actually being connected, and you have multi-drop. So as a message leaves the modem, it goes through the different ones, and message is being received by different PLCs. As an example of a SCADA system implementation, also in the book, here we saw a primary control center, again HMI station, engineer workstation. You have your SCADA, MTU here, the control server, and through a modem, you have some kind of connection to the field sites. Right here, they mention RF, radio frequency communication. So using this communication medium, you can connect to your field sites, right? They have on the other side, they have to have an antenna that will receive the message, demodulate it, and then it will go to the command, will go to the RTU that is controlling the remote station, something like a valve or a pump, and then it has the corresponding sensors, level, pressure, or flow sensor. So in a SCADA system, you have here another remote station. This station is connected in series with another station. So you can have from here to reach your control center, you go through this remote station and all the way back. So this SCADA system is collecting information coming from the various remote stations or the field sites here, right? And gets everything here in the main control center, and the human operator can choose to make decision about what can the action be. So there is also control happening. There is data acquisition coming from the sites, but there's also control from the control center to the individual sites. And here, as an example, there's also a regional control center connecting through a wide area network. Here we have our corporate network also appearing here. You may have some kind of more complex connectivity through some kind of a wide area network connected both the regional control center and the primary control center, again, to another remote station with sensors and actuators. So this is an example of a SCADA system implementation, and the example is useful to start understanding all the different attack vectors that an adversary can use. You have, for example, you can jam the communications here, or you can, these are locations that can be unmanned, so you can maybe break through the door and try to access the RTU physically there. This is a good example. You need to understand the topology of your system very well to be able to start the risk management process appropriately, and then you follow with your ICS security architecture. So SCADA, as I said, is mainly used for dispersed assets, right? The fact that you connect from one site to geographically dispersed assets that can be located very far away. DCS stand for Distributed Control System, and DCS are primarily used to control production systems within the same geographic location. So a power grid was a good example of geographically dispersed assets. Oil refineries or chemical manufacturing are examples of production systems that happen within, let's say, one building, right, or within one location that is geographically enclosed, and you can have physical controls, and you don't need to have these remote telemetry capabilities that we've been discussing before. So DCS are integrated as a control architecture containing a supervisory level of control overseeing multiple subsystems. So you can think of DCS, here I have an implementation example in this slide, again from the handbook. So all this, the slide is within one location, right, one geographical location. So DCS has distributed control systems. Here you see you have your, there's a PLC here, there's a different process controller, a single loop controller, and there's a control network that the HMI is connected to. There's a historian, a workstation, another controller controls another part of the process. So you see they're independent parts. This part is independent. You have your PLC on its own field bus. You have another controller on a different field bus with different sensors and actuators. You may have a series connection to a remote access here that can be in field connection from the engineer. Another controller that can be remotely accessed as well. So here, they may be different parts, but they are they're distributed, but they're connected through kind of a local control network that goes all the way to a main link here, workstation, application server, OPC, and so on, that may or may not connect to the enterprise network, or you may connect to the internet, right? And well, of course, this comes with its own security problems. So DCS, again, the big difference is that this is a geographically confined system, and you have different security challenges for a DCS compared to a SCADA system. PLC stands for Programmable Logic Controller, and the term PLC, will use it a lot. Sometimes you may see the term IED, Intelligent Electronic Device. These terms may be used interchangeably. I'll be using the term PLC a lot, referring to these controllers that can be programmed, and PLCs are computers in a way, are digital computers, but they're being hardened. They have been adapted to work in the manufacturing process. Adapted means they can work in different temperatures that are regular computers, maybe minus 20 Celsius and up to 60, 80, 100 Celsius, depending on what the exact process is. They're more robust to faults, so they have more fault tolerance, they have maybe error correction in memory. So they are computers in a way, but they're not your regular consumer computer. They have been adapted for manufacturing. So, and besides this adaptation that we discussed about temperature or withstanding electrical voltages above the expected range you have in a house, you also have a lot of input and output. Our computers, our input-output is keyboard and mouse and screen. In a PLC, we'll get inputs from sensors, could be temperature sensor, level sensor, flow sensors, and will also be connected to an output, connecting a valve or a furnace or some kind of a actuation device. So besides being hardened, they also have a lot of analog interfaces that they can bring in analog values from the physical world, process them, and then respond back with some kind of action to the actuator to control the physical process. So these devices can be, the PLCs can be just small devices with tens of inputs, or can be hundreds of inputs, like rack-mounted PLCs, and they can also be networked to other PLCs or SCADA systems. And PLCs, we saw SCADA and DCS before, right? But you have a small process, a small control system. You can even have it controlled by a single PLC. So PLC doesn't mean you have only one control loop in it, but it can do many things in parallel, and it can do things depending on how many inputs are coming in and how many outputs it's actually controlling. So in SCADA and DCS, you can think of a central control system that you observe, and actions in the system may be more human-driven in a way. A PLC is more automatic, so PLC will respond by itself, so it has a control logic. It's a more closed-loop control without human involvement. So that's also a big difference, right? If a PLC is attacked, a PLC has been designed to be responding automatically to process changes, while SCADA may, the effect could be only providing wrong information to the operators, and the operators may suspect something may be going wrong with the data acquisition systems. So there's also a big difference in thinking about security of SCADA and DCS compared to PLC. In this slide, I have another control system implementation. Actually, we saw that in DCS in a part of the DCS system, but here you have a PLC controlling everything, right? The PLC, there's an industrial protocol here, field bus, and you have your sensors and your actuators connected to it, and also the HMI can be connected directly on the field bus and the PLC, so you can get information about what's happening in that control system, right? But again, a PLC configuration, PLC control system implementation is more suitable for smaller control systems. So with that, we conclude the discussion about terminology. We started discussing the difference between IT and OT, and then we saw industrial control systems and examples of industrial control systems as SCADA, DCS, and PLC. So here I have a rough depiction of the relationship between all the systems. So in a way, DCS, PLC, and SCADA are included in the term ICS, that in turn is included in the term OT.